introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 45-50 minutes, followed by time for questions and discussions. Please feel free to type your questions or comments at any time in the meeting chat. Don't necessarily wait until the end. So it's my great pleasure to introduce our today's speaker, Professor Ben Green from University of Oxford, UK. Professor Ben Green is a great mathematician whose work spans additive combinatorics, number theory, and related areas. He is widely known for groundbreaking contributions, such as the Green-Taus theorems about arbitrary long arithmetic progressions with the prime numbers, and many other great results. And he has received numerous awards in recognition of his influence on modern mathematics. In this talk, he will discuss the polynomial Freiman-Ruzsa conjecture, outlining its background, key ideas, and recent resolution, as well as its role in shaping current research in additive combinatorics. So I'm now happy to hand over to our speaker.
Okay, thanks very much, Bogdan. And just to say, I think if people ask questions in the chat, I might not be able to see them.
I will let you know. I see the chat, okay. I will let you know.
Yeah. Okay, so thank you very much for inviting me to speak, Bogdan. And I'm going to speak today about polynomial Freiman-Ruzsa and Martin's conjecture. So this is to do with what we call subsets. And I'm going to start just by giving the definition and some examples of what subsets are. So suppose you've got two sets A and B, which in this talk are going to be finite, and they live in an abelian group. Then you can define the subset A plus B to be the set of all sums of pairs of elements, one in A and one in B. And you can define the subset of a set with itself, A plus A, which is the set consisting of sums of pairs of elements of A. So here are a couple of examples in the integers. If I take my set to be the numbers 1, 2, 3, 4, and 5, then the subset is the numbers from 2 up to 10. Anything in that set's a sum of two elements of A and nothing else is. And a different example would be if I take the first 5 powers of 2, then I get a much bigger subset. That's the set of things that are the sums of 2 powers of 2, which has a smallest element 2 and various other elements up to 32. So hopefully the definition is quite clear. A lot of classical problems in number theory can be stated using the language of subsets. So to give you a couple of very famous examples, Lagrange's theorem states that every number is the sum of 4 squares, every positive integer is the sum of 4 squares, and you can state it in this sumset notation. S is the set of squares, then S plus S plus S plus S is everything. And equally famous theorem is the Ternary-Goldbach theorem. If I take the set of primes, then the triple subset P plus P plus P contains all odd integers at least 7. And that's a rephrasing of the fact that every odd integer greater or equal to 7 is the sum of 3 primes. This notion of subset isn't just restricted to number theory. It's also very relevant, for example, in analysis. It's very closely related to the notion of convolution of functions. If I've got a function f that's supported on a set A and another function g that's supported on a set B, then the convolution is going to be supported on the subset A plus B. So it's a pretty central notion in a few different areas of mathematics. Okay, what can we say about the size of these subsets? I showed you 2 examples at the beginning of a set A with 5 elements, where the subset can have rather different sizes. In general, if you've got a set of size n, then this inequality is going to be true. The subset's got size at least 2n minus 1, and size at most the nth triangular number. Now, the lower bound is not completely trivial. It's quite a fun exercise to try and prove that, which I'll leave you to think about. The upper bound is fairly trivial. This just comes from the fact that x plus y is always equal to y plus x. So you lose a factor of 2 over the most trivial bound, which would be n squared. So actually, the 2 examples I gave right at the beginning are tight for these lower and upper bounds respectively. So the first example I showed was an arithmetic progression of length n, the numbers 1, 2, 3, 4, 5. And in that case, the sum set will be another arithmetic progression of length 2n minus 1. And the other example I showed you, the first 5 powers of 2, well, that has the property that the pairwise sums x plus y are always distinct, apart from when x plus y equals y plus x. So they're as distinct as they possibly can be. So those two examples saturate the inequalities. Actually, another nice exercise is to show that the only situation where you can get equality in the left-hand side of the inequalities at the top of the slide is when you have an arithmetic progression. So this sort of non-trivial fact there. So I'm going to be mostly talking about sets with small subset. And let me frame what that means. So I'm going to be fixing some number k. Might be, you can think of k as being, say, 10 throughout the talk, if you like. And let me take a set of size n, and I'm going to think of n as being large, much bigger than k. And I want to know what is the structure of A if the size of the sum set is not that much bigger than the size of A. So we call the ratio of A plus A divided by A is called the doubling constant. So what can I say about set A if the doubling constant is bounded by this number k? In that situation, we say that A has doubling at most k. Here are some examples that go a bit beyond just arithmetic progressions, which have small doubling. This object P that you can see on the slide is a kind of d-dimensional grid projected down to the integers. And here's a picture of an example of such a thing. So there's a set of integers illustrated at the bottom there. That is what we call a generalized arithmetic progression of dimension 2 and of size 15 in this case. So just to relate it to the definition that I wrote, the base point, what we call the base point, x naught here, would be minus 11. And then the elements of P are a grid sort of based on minus 11 with two different directions or lengths, 1 and 9. And then I can take various combinations of those up to these thresholds. So that's what these generalized progressions look like. And anything like that will be an example of a set with small doubling. So that sort of a progression will have its sum set at most 2 to the power d times the size of the set. And very often equality will occur there, but there could be some overlaps which would make the doubling less. Other examples of sets with small doubling would be to just take one of these generalized progressions like the one pictured and just throw away half of the elements. So then it doesn't look quite so structured. It's like a grid with some holes in it, but it will still have a small or fairly small doubling constant. And there's this really remarkable theorem of Freiman. So here's a picture of Freiman on the left. Sadly, Freiman passed away in 2024, aged 98 though. And on the right is Freiman-Ruzsa. I'll say why his picture's there in a moment. So this is what we call an inverse theorem for sets with small doubling. And it basically says that the example that I just told you is the only sort of example of a set with small doubling. So here's a precise statement of the theorem. Suppose I have a subset of integers of doubling at most k. The sum set A plus A is at most k times the size of the set A. Then the conclusion is that A has got to be contained in one of those generalized arithmetic progressions. And the dimension of that progression is bounded only in terms of this k. And also the size of the progression is not too large either. So Freiman proved this in 1966 in a book which is really very challenging to try and understand. Ruzsa in 1994 gave the first accessible proof of this, which also gives fairly good bounds for these quantities d and c. So sometimes this is known as the Freiman-Ruzsa theorem. Now, this talk is not really about integers, but rather about what we call finite field analogues. And these are analogues of the sorts of questions that I've just described, but where the integers are replaced by vector spaces over fixed finite fields. Now, Fp is a finite field with p elements, and you look at the vector spaces Fp to the n over there. And typically, P would be some small fixed prime like 2 or 3. So why would we look at such things? One key reason is that the phenomena that we're looking to understand are often much cleaner and have simpler proofs there. And moreover, if you can find proofs in these finite field settings, they will often give you hints about how you should proceed over the integers. But also, happily, these finite field questions can often be interesting in their own right, particularly in the binary case, p equals 2, where there's been quite a lot of interest in theoretical computer science in the questions that come up. So there's a key difference in these sort of finite field models in that you can have very big sets where the doubling constant is just exactly 1. So f2 to the n has many subspaces that are just completely closed under addition. So if you take A to be one of those, then A plus A will be the same set back again. So it has doubling exactly 1. And actually, you can show that's almost an if and only if. So the only sets with doubling 1 are cosets of subgroups. So we can ask exactly the same question in finite fields. What is the structure of a set A? If A has a doubling constant at most k, but now this set A is in this finite field model f2 to the n. I can ask the same in f3 to the n and other fp to the n, but mostly I'm going to be focusing on f2. And Ruzsa was the first person to prove an analog of Freiman's theorem in this setting, and moreover with a much shorter and very clean proof. So he proved the following theorem. The theorem is that if I have a subset of f2 to the n with doubling constant bounded by k, then the only way that can happen is that A is efficiently contained in a genuine subgroup H. So there are no kind of multi-dimensional progressions because we're in a group with 2 torsions, so those would all just wrap around again. And the only things that you have are subgroups. So A is contained in a subgroup H of size at most a function f of k times the size of A, and the f of k is just a kind of exponential in a polynomial, so not too bad. I'm going to show one proof in this talk, and it's going to be this one. So I'm going to just very briefly sketch the proof of this theorem, assuming, well, at least one fact that I'm going to just state. So here's the sketch proof. You look at 3A, which is the sum of 3 copies of A, and take X to be a maximal subset of that, such that the translates of A by the elements of X are disjoint. So everything's finite, so there will be a maximal such set. Maximal means you can't add any more without destroying the disjointness property. Okay, so the size of A times the size of X is at most the size of the 4-fold subset of A, because all of those translates A plus little x, they live in the sum of 4 copies of A. I've got 1 copy of A, and then the x's lie in the sum of 3 copies of A. And here's the thing I'm going to quote. There's something called the Freiman-Ruzsa inequality that gives you a bound for the 4-fold subset of A, assuming that A has small doubling. So we know that that 4-fold subset has size at most k to the 4 times the size of A. So this set X is bounded in size. Now, what does the maximality hypothesis mean? It means that if I take another element T of the 3-fold subset of A, then A plus T intersects one of those A plus X's. That's just the maximality. And if you rearrange that, and I think here I'm using the fact that we're in characteristic 2, so plus and minus are the same, you get that T lies in A plus plus this element X. So because T was arbitrary, what I've shown is that the 3-fold subset of A is contained in the 2-fold subset of A plus this fixed set of X of translates. So once you have this, you can then just add copies of A to both sides. It's like doing very simple algebra. So the 4-fold subset of A is contained in the 3-fold subset of A plus X, which is contained in the 2-fold subset of A plus 2 copies of X, and so on. You just keep adding copies of A. And you eventually conclude that the set of the entire subgroup generated by A, which is going to be is the union of all of the subsets of A, is contained in A plus A, 2A, plus the group generated by X. However, we're in a finite field, so the group generated by X is just the set of 0, 1 combinations of elements of X, which has size at most 2 to the power of the size of X. And I know what the size of 2A, or A plus A, is. It's K times A by assumption. So what I've got is an upper bound on the size of the group generated by A. And I may as well take my H to be exactly that group. All right. So that's really the only proper proof I'm going to give in the talk. That's pretty much a complete proof if you believe this Plunker-Ruzsa inequality, which is not so hard to prove. Okay, so let me just quickly remind the statement. So the statement of this theorem of Ruzsa is that if I've got a set A of doubling at most k, then it's contained in a subgroup. However, you lose an exponential factor, in fact, slightly worse than that, 2 to the k to the 4, in making that statement. And actually, some exponential loss is necessary in this kind of a statement. But Martin conjectured that there's a slightly variant version of this statement where you don't lose this exponential. And here is Martin's conjecture. Again, suppose I have a set A in f2 to the n with doubling constant at most k. Then what she conjectured is that rather than trying to put all of A inside just one subgroup, I can put it inside a few cosets of a subgroup H. And then I can try and make that subgroup much smaller. So specifically, she suggested that you can take the subgroup to be of the same size or smaller size than the size of A. And the number of cosets you need should be just polynomial in K. And one also conjectures that something similar should hold for any fixed finite field. So the characteristic 2 case became known as Martin's conjecture, or the polynomial Freiman-Ruzsa conjecture, which is the term that was used more frequently when we're talking about general characteristics. So that's a picture of Catlin-Martin there. So one thing to say about this conjecture is that if true, it's almost an if and only if. If you have a set that is a union of k to the c cosets of a group H, then the doubling constant of A is at most k to the 2c. Okay, so you've lost something in the exponent of the polynomial, but it is only a polynomial loss. So up to polynomial losses, this is a complete description of sets with small doubling. Now, this was probably my favorite open question for a very long time, 20 years or so. And why was I so keen on it? So that's just a repeat of the conjecture. First of all, it's a very clean statement. But another reason that it was interesting to me is it has many non-trivial equivalent forms. I'm going to mention 2 of those. First is this very beautiful statement that Ruzsa showed me, which is that conjecture of Martin is equivalent to a statement about almost linear functions. And what this statement says is if you have a function between 2 vector spaces in characteristic 2 that's almost linear in a weak sense. So if I look at the set of values taken by f of x plus y minus f of x minus f of y, now if f was completely linear, that would always be 0. But suppose that it just takes a fixed set of values of size at most k. Then the claim is that it's a stronger kind of linear function, namely it's a perfectly linear function plus a function that takes only a small number of values. So weak linearity implies a kind of stronger linearity. And Ruzsa showed that that statement is completely equivalent to Martin's conjecture. Now, the other thing I want to highlight, and this will mean something maybe to some people in the audience, there's a very fundamental thing in additive combinatorics called the Gowers norm. And there are different flavors of Gowers norm called the U2 norm, U3 norm, U4 norm, and so on. The first one that's really goes beyond classical Fourier analysis is what we call the Gowers U3 norm. And it kind of measures quadraticness of a function f. It looks at third derivatives of f and looks at whether there's some sort of a bias involving them. And this comes up whenever you want to study arithmetic progressions of length 4 or longer, or other types of linear pattern. And this was a fundamental thing in my work with Terry Tao on primes, for example. So it was shown by Terry Tao and myself in about 2009, and by Lovett at the same time, that what we call an inverse theorem for this Gowers norm. So if this, what we call the U3 norm of a function is large, then the function correlates with a quadratic phase. A polynomial version of that theorem, which is, I think of as sort of the foundational theorem of higher order Fourier analysis, is again equivalent to this conjecture of Martin. Okay, so I'm not going to explain any of those terms in any more detail, but I just wanted to say that it's linked to something that came up in a huge amount of my other work and work of other people as well. Now, let me just talk about progress on the problem before the work that I want to discuss for the rest of the talk. I've already mentioned Ruzsa's work. Ruzsa showed that if A has doubling K, then you can put the whole of A inside just one subspace H of size 2 to the K to the 4 times the size of A. So that's already some progress towards Martin's theorem. But there was significant work by Tom Sanders, refined by Koniagin, who got much stronger bounds like that, what we call a quasi-polynomial bound. So it's not polynomial, it's not K to a fixed power, but it's e to the log K cubed or something like that. Okay, so now let me turn to the main result I want to talk about, which is this solution of Martin's conjecture. And this was done by Tim Gowers, Freddie Manners, Terry Tao, and myself 2.5 years ago. And the theorem is that Martin's conjecture is true, and the number of cosets that you need is actually bounded by K to the power 12. And that 12 was quite quickly improved down to 9, quite soon after we proved that. So I'll talk a little bit about the proof shortly, but let me just mention some consequences of this as well. So of course, the equivalent forms that I mentioned, they're equivalent to it, therefore we know all of those as well. So we have a polynomial inverse theorem for the U3 norm, for example. It is also known by somewhat earlier work of Freddie Manners, Terry Tao, and myself to imply a result over the integers that we call the weak polynomial Freiman-Ruzsa over the integers. And that says that if I have a set A in, it could be in just R to the D for any D, and it has doubling at most K, then a large piece of A has really a small dimensions, bounded by log K essentially. And then I just want to mention an application quite a different type by Akshat Mudgal. This is a nice kind of sum product theorem over the reals. Now, if you just take any finite set of reals, provided it's got at least 2 elements, and if you look at summing m copies of A plus A plus A m times, or taking the product of m copies of A, which has a very similar definition, at least one of those two has got to be way bigger than the size of A. So if I pick m large enough, that one of those two sets will have size at least A to the 1000. So that's a very non-trivial application of what I mentioned before. Okay, so in the remaining 20 minutes or so, I'm going to talk a bit about the proof of this Martin conjecture, but in quite general terms. But the fundamental idea is to do a kind of induction on the doubling constant. So here's the rough idea. Suppose I'm given a set A where the doubling constant is K. So the size of A plus A is at most K times the size of A. What we'd like to try and do is find another set A dashed where the doubling is a bit smaller, and somehow this A dashed is also quite related to A. I mean, it's no good finding a completely unrelated set A primed. Otherwise I could just take A prime to be just some random subspace. But we want to find something with slightly smaller doubling that's kind of a bit related to A. That's the basic idea of the proof. And maybe that won't be possible. We'd like to show that if that's not possible, then actually you've got a set with doubling very close to 1. And we know there are earlier results, actually other results by Freiman from the 1960s that tell you that in that case you are close to a subgroup. So another way of thinking about this is you're going to somehow repeatedly refine the set A to A dash, then A double dash, and so on. and eventually end up with a set where the doubling is close to 1, at which point you can conclude it's a subgroup. So that's the very rough strategy. The key question then is, how should I find this A dashed? And there are two main ways to try and select the A dashed, which I'll illustrate by example. So the first of those is called cutting. Now let me consider this example. So this is H here is a subgroup, and I'm taking a union of just M cosets of that subgroup. But think of those xi's as being quite dissociated. So these are very disjoint kind of cosets. This will then be a set with doubling constant k, roughly k. All right, so there's some kind of a picture of what this looks like. I'm supposed to be in a finite field, f2 to the n, but this is a kind of indicative picture of what a set that's a union of 3 cosets would look like. So how would I find a set A primed that's somehow related to this, but has much better doubling? Well, I think it's reasonably clear what one would like to do. You just want to pick one of those cosets. So that's what we'd really like to do. Take A prime to be just one of those, say H plus x1. This is then related to A. It's 1/3 of the set A, but it has doubling constant 1, so it's much better than A. All right, so it's not at all obvious if I'm just given a set A that isn't this example, how one might try and isolate this A primed. But there's an interesting feature here, which is that this A prime can be isolated in a way that's somehow intrinsic to A. It's equal to A intersected with a translate of itself. So it's A intersect with A plus T, where T is x2 minus x1. So this operation of taking the set A, shifting it by T, and then intersecting them together is called the cutting operation. And at least in this example, that is a way of improving the doubling properties of A. So that's called cutting. Now, there are other examples where that's not a good strategy. And in those examples, or in another example I'm going to show you, there's a different strategy that we try and use. This is called filling. Suppose now that I've got a different kind of a set. So now I'm going to take H, which is just a subgroup, and just take inside there a random set A. So you could literally just pick elements at random with probability 1/k. And almost surely that will have a doubling constant k, because the set A will have size of H over k, and A plus A will almost surely be the whole of H. So this is a highly schematic description of what that looks like. This A is a random subset of H. In this case, K would be something like 3. It's about 1/3 of H. And in this case, it's natural to take A prime to be just the whole of H. So that is, again, a set with much better doubling constant 1. And again, you can define this A primed in a way that's intrinsic to A. So the intrinsic description is that A primed is equal to A plus A. So again, if I showed you a set A and told you that it's a random subset of some subgroup H, how would you reconstruct the H? I claim the best thing to do would be to just look at A plus A, and almost surely that's going to give you the H back again. So taking A and replacing it by A plus A is what we call a filling operation. So we have cutting, which is shifting and then intersecting, and we have a sum-set operation that we call filling. So here's a more sophisticated variant of the inductive strategy. We'll start with our set A, which has got doubling at most k, and then we'll try and either cut it or fill it and hope that that will improve the doubling properties of the set A. And then provided we can sort of keep track of this sufficiently well, that might allow us to prove Martin's conjecture by induction. Okay. Of course, that's hardly even a strategy at the moment. We've got to, first of all, prove that either that cutting or filling does improve things, and then figure out how we can recover Martin's conjecture. But that's a sort of vague idea of a strategy that one can hope to use. Now, there's a heuristic which suggests that this isn't a completely terrible idea. So let me show you the heuristic. Suppose I've got a set A of doubling constant k, and then we'll look at the Cartesian product A times A. So it's just pairs of elements of A in the product space f2 to the n cross f2 to the n. So the sum set of this is just the product of the subsets. So that has doubling k squared. Now I'm going to consider the projection from this product f2 to the n cross f2 to the n down to just f2 to the n. But it's not going to be one of the two coordinate projections. It's going to be the x plus y direction. So let's consider that homomorphism, pi of xy equals x plus y. This set A times A pushes forward under that pi to give the sum set A plus A. So I'm going to call that's the base, that's the image of the homomorphism pi. And then there are some fibers, which are the inverse images of points T. And those fibers are basically going to be translates of A intersect A plus T. So I've written this A times A as a kind of fiber over a base, which is A plus A, with fibers. So the base is the filling of A, and the fibers are the cuttings of A. Okay, and it's kind of reasonable to think that the doubling of A cross A should be something like the doubling of the base times something like the doubling of the fibers. So that's literally true when I've got a Cartesian product like the original A cross A, but I've now kind of rotated this at 45 degrees, if you like, and I'm hoping that something similar will still be true. So that's just a heuristic, but at least says that this is perhaps not a completely silly idea. Right, but let me tell you some things that go very badly wrong if you try to turn this heuristic into a proof. So it's far too simplistic, and actually really bad things can happen just if you take a set A with small doubling and try and push it down under a homomorphism. You can construct examples where that actually increases the doubling constant. Seems counterintuitive. You might think if you take like a sort of rectangle or something and push it down, the image will be just an interval which has a smaller doubling. But there are examples where that's not the case. And really the main problem is that we're not thinking about the problem the right way. And this is something that's well understood in many parts of maths. If you're doing these sorts of fibering arguments where you're pushing things forward under homomorphisms, you shouldn't be restricting yourself to just working with sets. You should really work with measures. And let me try and illustrate that. So let me consider this 3-element set consisting of 3 points in Z squared. And it's just 3 points forming a triangle, 0, 1, 1, 1, 1, 0. And then consider what happens when you push that down to the integers. And as a set, that contains just 2 elements, 0 and 1. But it's clearly more natural to weight the element 1 twice as heavily as the element 0, because 2 of those elements push down to 1 and only 1 of them pushes down to 0. So really what you want is that this pi of s should not be a set, but rather this measure that assigns a weight 1/3 to 0 and 2/3 to 1. So it's not the uniform measure. So once you've had this idea that really one should be working with measures, you can then go back and think about the whole heuristic sketch that I just outlined and think about how that might work in the more general world of measures. And to even begin, you need to define what is the doubling constant of a measure. Now let me take some probability measure on a group G, and really, so that's just, I'm going to think of that as finitely supported. So it's really just a function taking values between 0 and 1. And the fact that it's a probability measure is just saying that the sum of mu of x is just 1 everywhere. Another way to think of that is as a discrete random variable. So x is a discrete random variable, and the probability that big X equals little x is mu of little x. So how do I define the doubling constant of a random variable? Well, we do it using entropy. I haven't written on the slide what the definition of entropy is. You don't really need to know to follow the rest of the talk. What it is, it's the sum of minus p of x log p of x, where x ranges over the domain of the variable x, and p of x is the probability that capital X equals little x. Another way to think of it is it's very roughly log the number of points of log the number of values taken by the random variable x, but with a kind of account taken of the weighting. So we can define this, what we call the entropy doubling. You basically form the sum set of this random variable x, which is another random variable. You take two independent copies of x, call them x1 and x2, add them up, that's another random variable, and you take the entropy of that minus the entropy of the original variable. This is something that's called the entropic Ruzsa distance. Well, you can define more generally the entropic Ruzsa distance between two different random variables x and y in a very similar way. So if I've got random variables x and y, I first of all take two independent copies of them because the x and the y might not be independent. And I look at the sum set x dash plus y dash, take the entropy of that and subtract off the average of the entropies of x and y. So we call it the Ruzsa distance because it satisfies this quite nice triangle inequality that was discovered by Ruzsa in this context. So summary of that slide, there's a certain kind of analog of sum set doubling in the more general context of measures. It's not quite the same thing as the doubling constant of a set. So if I have a set A, I can associate to it a random variable just by picking elements of A uniformly at random. So that's called the uniform distribution on A. And then this entropic doubling constant is not going to be exactly the same as the combinatorial doubling constant, but it's closely related. So actually the e to the power of this entropic doubling constant will always be less than or equal to the combinatorial doubling constant, but also greater than or equal to another kind of a combinatorial object, which is related to the number of coincidences of pairs of sums. So one should think of it as something very closely related to the doubling constant that admits a natural generalization from sets to measures. And this, I believe, is somehow the correct way to be talking about these problems. So once you see that this definition can be made and has nice properties like the triangle inequality, it really starts to seem very natural. Okay, so what we actually do is prove a version of this Martin conjecture for general probability measures, and then recover the formulation for sets as a special case. And here's how it looks. You take any two random variables x and y on f2 to the n, and then the statement is that suppose I know that the distance between x and y is small, then the distance between x and a uniform random variable on some subgroup is small. And you can just write this as an inequality that I've written here. So the distance between x and a suitable subgroup is bounded by 6 times the distance between x and y. The original statement involving sets can be shown from this in a fairly straightforward way. You need a few entropy inequalities. So in this more general context of measures, the heuristic I mentioned before, where you take the Cartesian product and consider pushing forward onto the base and looking at the fibers, that can actually be justified completely rigorously. So in the context of measures, either the cutting operation, so in other words, looking at the doubling constant of the fibers, or the filling operation, which is the doubling constant of the base, one of those two will not increase. The proof of that, and in fact the proof of almost everything in this entire subject, is just some combination of the basic properties of Shannon entropy, and in particular something that's called the submodularity inequality, which essentially says that the entropy of x conditioned on y is at least the entropy of x conditioned on y and z. So somehow knowing more information decreases the entropy. So you end up with fairly long chains of inequalities involving these basic submodularity inequalities. Okay, but it turns out there's actually a problem with the whole strategy that I outlined, which is that you can have an example where, so we know that either the cutting or the filling operations, one of those two doesn't make things any worse, but it may be the case that neither of the two of them make things strictly better. So remember, we're trying to do an induction. We need to go from doubling k down to something that's a strictly smaller doubling. So here's an example of what can happen. Suppose now that I've got the following kind of a set. I'm going to take a subspace H and consider the union of m cosets of H, where m is something like square root k. And instead of taking all of those m cosets, I'll take a random subset of the union of those cosets. So this is the kind of thing that it looks like. So I've got m cosets of this subgroup H, and inside each one, I pick a different random subset. And that's my set A. So that will have doubling constant k. And in fact, the filling, so A plus A, is going to look a bit like this picture. So what happens is that you pairwise add these cosets. So I get all of the x plus hi, sorry, h plus xi plus xj. And in each one of them, the random sets that I'm adding together will kind of fill out everything. So you're going to end up with a rather larger set of cosets, m squared of them instead of m, but with all of each one. However, that still has doubling constant k. Now, what does the cutting look like? So if I take that set A and intersect it with a translate of itself, well, it has one advantage, which instead of having m different cosets, I only have one coset, but I have a much smaller portion of it. So I basically, this is what happens from intersecting h plus x1 with a shift of h plus x2. The two random sets inside intersect to give a much smaller random set. So that still has doubling k. So in this case, I've got a set with doubling k where both the filling and the cutting still have doubling k. And that seems to defeat the whole strategy that I'm trying to make work. However, you can note that if you do cutting, so produce the set that's in the picture just above the bottom line, but then do another filling, so that this cutting, it will be a random subset of h plus x1, okay, a fairly small density like 1 over k, but when I sum it to itself, I will still get the whole of h. So if I do cutting and then filling, I get a really good set h, which now has doubling 1. So although the first strategy I suggested is defeated by this example, a slightly more exotic strategy where I'm allowed 2 of these operations in sequence could still work. And that's actually exactly what we do. So here is a sort of summary of the proof. So you start with a set of doubling k, and actually you're going to need to work with general probability measures. And then you try to either improve it by filling or improve it by cutting, so to reduce the doubling constant. Or it turns out you can do cutting and then filling. And what we show in our paper is that one of these 3 things will significantly improve the doubling. Now, one thing that I think is interesting about this is that most of what I said works in any group, except for this very last step, the fact that cutting followed by filling will significantly improve things if neither of the first 2 operations does. And that really crucially uses characteristic 2. And actually, there are examples over the integers of kind of Gaussian measures where the filling and the cutting will still be Gaussian. And so you definitely can't hope to use this strategy because you're just not close to a subgroup. Okay, so that's pretty much all I'm going to say about the proof. I mean, there's obviously a lot of detail in the proof. This was just a very heuristic overview. A lot of entropy inequalities, particularly submodularity, something called the entropic Balog-Semerady-Gowers theorem. But that's basically how the proof works. So just to conclude, I want to say a little bit about what's left open in this domain. The main thing that's left open is to solve the polynomial Freiman-Ruzsa conjecture over the integers. So what I just said really at the last step fundamentally involves being in finite characteristic. But what we believe is true is the following. So we believe that if I've got a set of integers a with doubling k, then you can cover it by a small number of what we call convex progressions, whose dimensions are just logarithmic in k and of small size. So these convex progressions are things that look like this. So something like The picture I've drawn here is in the plane, but you can project this down to the integers. So that's a conjecture. And currently, we don't know how to prove that. However, there's been recent progress by Ragavan, a student of Terry Tao, and Ragavan has kind of, in a very nice way, combined some of the ideas that I talked about in this talk using entropy with some more classical ideas of using Fourier analysis. And by combining the two, he's managed to get pretty close to this polynomial Freiman-Ruzsa conjecture. So he hasn't got polynomials, and he hasn't quite got logarithmic dimension, but he's losing basically just a double log in k in his theorem. So that's a very nice development. Okay, and that is the end of my talk.
Okay, thank you very much. So everybody, you can now unmute yourself and ask any question in voice if you like. Or if you're too shy to ask in voice, you can still write a question in chat. And I will read from the chat everything you ask. Yeah? Okay, I will start with my questions. So you have some more recent paper when you proved much more general theorem about any group with bounded torsion, yes, which was not mentioned here. So can you talk a bit more on that?
Yeah, so I guess we have an analogous theorem, for example, in fp to the n for any fixed p. The exponents of the polynomials will depend on p, and they must depend on p. And the proof is quite a bit more involved. So you have to basically, essentially the whole proof has to be done with a p multiplicity. So instead of just taking sums of two things, you have to take sums of p things. And talk, instead of distance, you have to work with multi-distance. It's pretty complicated to explain. It can be seen as a generalization of the characteristic 2 case, but by no means a straightforward generalization.
What is the status of this paper? Is it submitted, accepted, published?
Yeah, I think it's published. Yeah.
This new paper about bounded torsions already published, yeah?
I believe so.
Okay, I will have a look. So what about arbitrary abelian groups? You mentioned for Z, it's convex progression. Can you explain a bit more what is convex progression, because it's not clear?
Well, okay, there will be, you've got to be quite careful with the definition. I mean, it's something like, you know, a generalized progression, as I defined in my talk, could be thought of as the projection of a grid, like a box of points. And if instead of a box, you take an ellipsoid, ellipsoid should be fine. You don't need to worry about general convex shapes. So you look at the lattice points inside an ellipsoid, and it would be the projection of that. Now you have to be quite careful. You have to be a little bit careful that you don't accidentally take an extremely flat ellipsoid or something like that.
And this works not only over arbitrary abelian groups. Something like this, yeah?
No, so I don't think anyone's written down the general conjecture. The general conjecture would be something like probably like what we call a coset convex progression. So it's some sort of a hybrid of a subgroup and one of these convex progressions.
Okay. What about non-abelian groups? So if you have like A plus A plus A is smaller than Ka in non-abelian group, can we still conclude the structure of A?
Yeah, there is a theorem that I proved in 2011 with Emmanuel Broyard and Terry Tao, which at least gives a qualitative answer to this. So there's the examples are the same subgroups and these sort of generalized progressions, but there's a new kind of nilpotent object that comes up called a nil progression. In some non-abelian groups, there are much cleaner theorems. There's, for example, earlier work of Helfgott, who basically showed that, for example, in SL2FP, there are really an approximate group's got to be very close to an actual subgroup. There are lots of interesting questions still out there. For example, any quantitative version of the first theorem I mentioned is still an open result, an open question.
So you're talking about the case when a plus a less than ka, like grows linearly, yes? What if it grows a bit faster than linearly, like near linearly? So, yeah, what can be said in this case?
So if a plus a has size at most, say, a to the power of 1.01 in the finite field setting, then this polynomial, this Martin conjecture that we proved, already has some content. But if you're interested in, for example, what can I say if a plus a has size of a to the 3/2, then what we proved doesn't have any content. There's a paper by Alex Cohen and Dima Zakharov that uses some of these entropy ideas to say something non-trivial with even with doubling close to size of a squared. But it says something, but it's definitely not an if and only if.
Yeah, 1.1 is already interesting. Yeah. Okay. So anybody else? Any questions you want to say in voice?
Well, I have a question, sir.
Yeah.
Yeah. First of all, thanks for the great talk. And well, I understand that the notion of the sum set is important in the many questions in number theory, and I understand that Martin's conjecture is about the finite set. So, is there any approach to prove the theorems like the weak Goldbach conjectures using the sum set?
Yeah, this is an interesting question. So, not that I know. I mean, yeah, people have speculated that, for example, you might be able to understand Waring's problem, bounds for Waring's problem. So you take the kth powers and add them some number of times, and you want to know how many times before you get a set of positive density.
Yes.
People have speculated that these sort of inverse subset questions could be useful there. I don't know of any direct implications like that. Yeah, so probably the answer to your question is no. I don't think I know of any direct implication between these sorts of results and the Goldbach problem.
So you mean that it is possible to interpret the problems in number theory in the world of sum sets, but there's not really a way to solve the problems using sum sets?
Well, not using these particular sorts of results. I mean, the main application, I mean, really the main reason that we've been thinking about inverse sum sets is because of the connection I mentioned halfway through the talk with what are called these Gowers norms. So Tim Gowers in the late 1990s uncovered a connection between these inverse questions and what are now known as Gowers norms. And that underpinned my work with Terry Tao on primes in arithmetic progressions and later work with Tao and Ziegler on linear equations in primes. So all of that work, the sort of core ingredient is coming down to these inverse questions for sum sets. But it's not so easy to explain exactly how that works, at least not in a talk that's primarily about sum sets.
Thanks.
Okay. Any other questions from anyone?
Ben, thanks for the talk. Could you say a little bit about your intuition for why this sort of entropic notion is the right generalization to more of a distributional viewpoint?
Yeah. So one way to answer that, there are two notions of structure that I guess people were primarily considering before we started looking seriously again at entropy in 2023. So I should say that these notions of entropy in additive combinatorics were first highlighted by Ruzsa and Tao in 2009, and they proved some interesting results, but they didn't make full use of it. So this sort of was revisited by me and Freddie Manners and Terry Tao in 2023. So the two previous notions which people have looked at are the combinatorial notion of doubling, so a plus a divided by a, and this notion of additive energy, which is basically the number of coincidences of pairs of sums. And they both have one advantage and one disadvantage. So the combinatorial notion has a nice kind of a triangle inequality associated with it, like this Ruzsa triangle inequality, but it doesn't behave well under projections. There are counterexamples to show that under projections, this doubling can even increase. And then the opposite is the case for the energy. So it doesn't have a triangle inequality, but it does behave well under projections. And the entropy has both of these properties at the same time. So it has these two quite desirable properties at the same time, and it's also quite closely related to both of those objects. I mean, the other thing I should say is that I don't think we could claim that we were the first people to introduce entropy in a related context as well. I think Kajmanovic and Vershik already in the 1970s were using similar notions of entropy in studying random walks. So it's something that's been, a standard tool in the random walk literature, which is not so very far away from the sorts of questions we're considering as well.
Thank you.
Okay, any other questions? Okay, if there is no more questions, then thank you again for your interest in talk. And yes, I will upload soon videos on YouTube.
Okay, thank you all for coming. Bye.